Anytime. There we go. Okay, so before we get started on our warm-up today, let's just do a quick refresher on how we're supposed to find local extrema. There's a lot going on there, right? You really actually have to find these critical points because that's usually where your extremas occur, right? Your max and your mins, right? And in order to find those critical points, we need to take the derivative, but then we also need to find out when is the function increasing or decreasing, which basically means we have to do the first derivative test, okay? So back over here last week when we were finished up this problem, right, we found the critical points, right? That's these guys down here, right? We found out the critical points to be equal to -3 and 1. And with those critical points of -3 and 1, that allows us to create intervals, right? Intervals that the derivative is going to be doing something in between those critical points, right? Without those, you'd be testing infinitely many points. But since we know that a critical point has a derivative of either 0 or is undefined, the derivative value between those ones will either stay positive or stay negative, right? The only times they can change is when they go through a critical point. Okay, so that's why that creates these three intervals. So if that all just sounds like too much to remember, just realize right here, if I have a critical point at -3 and another critical point at 1, the interval that I'm focused on here to see if it's increasing or decreasing would be some number that's between that, right? Some number that's between -3 and 1. And that's the, that's the interval that's between the two. And then you also have two other intervals. One interval that's above the last critical point and another one that is below the first critical point. So the more critical points you have, the more intervals you'll have to deal with, right? If you only have one critical point, you'll have two intervals, one above and one below. You have two critical points, you have three, and it'll go on so on and so forth, right? It all depends on how many critical points you're dealing with. Once you have those intervals, we would just test the number that's in those intervals and see if the number that comes out is either positive, right, negative, and that determines if the function is increasing or decreasing. And why do we care if a function's increasing or decreasing? If you're looking for a local maximum, that means a function needs to first increase and then decrease. And this critical point right here where the derivative is 0, you can see that that's a max, right? Because it goes from an increasing tangent line to a decreasing tangent line. Whereas if you have something that's decreasing then increasing, this critical point down here has to be a minimum, right? And again, the tangent line is going down, it's decreasing, and then over here the tangent line is going up, it's increasing. So when you have something change from decreasing to increasing, you have a minimum. If you have something changing from increasing to decreasing, you have a maximum. And it's kind of hard if you try to memorize that. It's easier if you just think about it. If you have something that's going up and then goes down, you can realize that that's like climbing up a mountain. They have a peak there at the top. Whereas if you have something going down and then starting to go back up, it's like going down into a valley and then coming back up at the bottom of a hill, right, which is your minimum. So that's the sake of how we're going to find these local extremas, right? So it sounds like a lot, and it kind of is. All it states is find all local extrema, but there's quite a few steps to do here, right? So let's go into it. So first things first, find the critical points, right? Find your critical points. In order for us to do that, we need to find the derivative. That's not how you spell points, knock me. Find your critical points. So everything we learned from last chapter, right? We got to know how to take derivatives of these functions. This one's just the power rule. There's nothing else, no product rule, no chain rule, no nothing like that. So let's go ahead and take the derivative of this guy and see what we get. We got here 3x is going to be, we're going to get x cubed is going to be 3x squared minus 3 over 2 times 2x, right? And the 2 and the 1/2 right there, they're going to cancel each other out. Let me simplify that a little bit further there. So I have here 3x squared minus 3x is our derivative, right? In order for us to find our critical points, though, we take our derivative and we set it equal to 0. Take your derivative and set it equal to 0. So you have your 3x squared minus 3x equals to 0. And you have a couple ways you can solve this, but right, when all else fails, always start off with trying to factor it first, see if it works that way. And if not, then we'll try other techniques to solve this quadratic, right? So factor this out. They both have both terms have a 3 in common and an x in common. So this is going to be 3x factored out. Inside here is going to be x minus 1. So with that being said, when is this thing going to equal to 0? I'm going to have it equal to 0 at x equals to 0, right? 3x is equal to 0. That's going to happen when x is equal to 0. Or x minus 1 is equal to 0, and that happens when x is equal to 1. So those are my two critical points. Right? I don't know if that's a max or a min yet, but I do know that the tangent line at those points is flat. Right? The tangent line at those points are flat. And that could be a max, could be a min, or it could be neither. That's also a possibility. Your critical point is not guaranteed to be a max or a min, but it has a possibility of being a max or a min. Okay? So that doesn't answer my question yet, does it? My question is still find the local extrema, right? So I'm going to go ahead and set up my intervals here. Right, I'm going to go over here and do so. My first critical point is at x equals to 0. My second critical point is at x equals to 1, right? Which gives me 3 intervals to deal with, right? 3 intervals to deal with. First interval, right, is from negative infinity all the way up to 0. The interval that's between the two is from 0 to 1. And the last interval that we're dealing with is from 1 to infinity. Now, to find out if something's increasing or decreasing, we don't plug it into the function itself. If you plug it into the function itself, right, the original function, that just tells you the output value. It doesn't tell you if the function is increasing or decreasing. The only thing that tells you if something's increasing or decreasing is the first derivative, right, f of x, f prime of x. So what I'm going to be doing here is testing a point that's less than 0 into the derivative. So I'm going to be looking here to plug in, someone pick a number that's less than 0 to plug into the derivative. What do you guys want to see? What's the number? -1. All right, Calvin, we're going to go with that. Right? -1. I'm going to plug it into the one that's simplified. You guys okay with that? You guys okay with that? Actually, sometimes some people like to plug it into the factored form because then you just see what numbers are positive and negative that multiply with each other. Oh, we got a lot of people typed in -1. All right, we'll go with it. Check this out. -1 right here, we're going to go ahead and end up with 3 times -1 squared minus 3 times -1, which gives me -1 squared is just +1. That's going to end up with a +3. -3 times -1 is also a +3. That's going to be a positive number, which tells me on this interval, the function is increasing. Increasing. Right? And if you want to be really specific, it's increasing on the interval of -infinity to 0. But I tend not to write that part at the bottom because I usually make my table so it's clear to see where the interval is, right? Or what the interval is when it's increasing or decreasing. All right, so that's that. Let's do it for the next one. What's the number between 0 and 1? What's the number between 0 and 1 that's going to be easy to plug in? 0.5. Do you guys really prefer plugging in as a decimal? Nothing, no judgment, by the way, no judgment. 0.5 is a good number between 0 and 1. 1/2, that's right, Calvin. Those are the same things, right? Now, my question is, do you prefer to square 0.5 or do you prefer to square 1/2? And honestly, it doesn't really matter. I'm just making conversation. I like fractions a little bit more. I like putting it as 1/2, but if you put it in as 0.5, I'm not going to mark you wrong, right? That's perfectly fine. I'm going to put this in as 1/2, and I'm going to put it in as 1/2 into the factored form. Okay, I'm going to put it into the factored form. Just check this out real quick. I know a lot of people 2/4. All right, Calvin. 1/3 also works, but yeah, 2/4, yeah. But I'm going to plug it into the factored form. And here's why. Here's why. Check this out. 3 times 1/2, and then the other thing that is multiplying with is 1/2 minus 1. Okay? And the reason why is this. When I plug it into this one, I can deal with this a little bit easier, right? Out here I have a positive number. I know it's a fraction, and I know you guys don't like dealing with fractions, but again, we don't care about the resultant, we don't actually care about the numerical value of it. We just care if it's positive or negative to see if it's increasing or decreasing for this, right? So what I can do is when I plug it in like this, I can see 1/2 minus 1 is going to give me -1/2. I don't care what that is, which is, it's just 3/4. You guys are going to be able to handle that, but it's a -3/4. And that's the main thing I really focus on, is that what we get is a negative result, right? Which tells me that the function is actually decreasing on this interval. My gosh, Nakmi, can you spell today? Yeah, it's decreasing on the interval from 0 to 1. That's the function, and that's what it's doing there. It's decreasing on that interval. So now that I see that the function is increasing on this interval and then decreasing on that interval, what can you guys tell me about x equaling to 0? What is that? That is a local what? If you see it going up and then it goes down, it is an extrema. It is. And what type of extrema is it? Monica's saying right there, it is a local max. Very good. Local max. Now, in your book, it might not say local. It might use the word relative, right? And keep that in mind. That is the same thing. Relative max, local max, right? That's just saying that it's the max of that particular area. We don't know if it's the absolute max, right? Those are the two other words that they use. So local max, right, is like it's right there. Whereas the max of all of the function, we call that a global or absolute max. Right? So just get those terms down. You'll see more once we do more of it. But let's keep going here. Let's finish up this last problem here. Someone give me a number that is between 1 and infinity. Anyone got a good number? What's a good number to test between 1 and infinity? 2? 2 it is. You guys like picking the small numbers, huh? So again, I'm going to show you what I mean by plugging it into the factored form. It makes it a little bit easier sometimes, but not always. Not always. But this time, I think it does. 3 times positive 2 times 2 minus 1, right? That hopefully you guys can see a positive number times a positive number times a positive number. This is going to equal to a positive number, which is telling me that this thing is increasing, right? This is increasing on this interval from 1 to infinity. So it's going up like that. So this is also a relative extrema, a local extrema, isn't it? It is this, but except this one though is going to be a local min. Local min. Yeah, that's right. As a local min. How are you guys feeling? You guys feeling all right with this? Does this kind of make sense? How to find all that stuff? Hopefully it does. Right? Hopefully it's not too crazy. Okay. But before we move on, let's just keep practicing this here. And see how you guys doing with this, how you guys feel about this. All right. So first of all, I'll pause here for a second. You guys have any questions or any concerns? Anything that I might have lost you guys while I was doing this problem? Anything at all? And if you're watching the recording, I'm sorry, you can't actually ask me. Well, you can always stop by my office hours. So you should write down if you have any questions and then stop by my office hours from 1 to 2, and tell me, hey, when you were doing this during your video, how did you figure out how to find this or that? Right? Please, please, please come ask me if you ever have any questions. All right, let's move on. I want to keep practicing this. So let's say we do another problem. Okay, let's try another problem here. Here we go. Let's say I was given this problem right here, and I was asked to find the local extrema. Find the local extremas, right? For this problem right here. This one's a little bit more ugly, isn't it? It's the function is equal to x squared minus 4 raised to the power of 2 over 3. Raised to the power of 2 over 3. So I'm going to clear out your pair deck. And I want to see you guys follow the same steps we just did right here. I'm going to give you guys some time here. And I do want to see you guys try this out. So I'm going to clear out your pair deck. You guys ready? It's cleared out. Try this problem. Try this problem. And if you don't know what to do, at least start off with seeing if you still remember how to take the derivative of a function like this. Right? That's a big part of calculus, right? We did like 2 whole chapters on derivatives, didn't we? And it doesn't go away, right? Even though we moved on to another chapter, you need to know how to take the derivative of things. And it's going to get, I don't want to say it like this. The functions are going to get uglier. They're not always going to be polynomials, right? They're going to be weird looking functions. And you need to be okay with that, right? You've learned all of them. You learned product rule, you've learned quotient rule, you learned chain rule. Now it's time to apply them and calculate these derivatives. So hopefully you guys are getting a good start on this one. Remember what rule to apply. I'm just going to tell you guys right now. Probably looking at a chain rule for this one. You have a function inside and you have a function outside. You're going to have to chain rule that thing to get your derivative. Excuse me. This makes me sad. Probably don't need these anymore. All right, let's see here. We got 9 whole students who started writing out. That's good. Are you guys just gonna do it right on there? That's perfectly fine. Okay. I want to go piece by piece with you, right? So the first one up, let's see if you guys can do the derivative. And can you guys write down the derivative that you guys got before you do anything else on there? Just tell me what's the derivative on this one. You guys got to know how to take a derivative of a function, right? So like I was saying, right, the inside function is x squared minus 4. The outside function is some stuff being raised to 2/3. You got to know how to take the derivative of this. What's today? Tuesday? The other thing I was supposed to check on you guys while you guys are finishing this up. Did I assign? Actually, I don't remember now. Did I assign you guys some AP College Board classroom stuff? I did. It was due today. Let me go take a look real quick. I think I assigned some videos for you guys to watch, didn't I? And then I assigned a couple problems. Let me take a look. All right. Let's see here. You got 3 videos to watch and then take a 4-question. 4-question is, it's called a quiz, but it's not actually a quiz. It's based off of completion. I hope I told you guys that. I hope. I think I did. Yeah, I did. Okay, sweet. Sweet. Oh, the videos were all on the mean value theorem, it looks like, right? Let's see, how many people watched this video? 10%. Out of this whole class, only 2 people watched it? Interesting. I think maybe you guys just forgot over the weekend. Same thing with the second video, same 2 people, and the third video, same 2 people. Interesting. How many people did the questions, though? That's also important to ask. Yeah, mean value topic questions. Four people did the questions at least. Okay. Yeah, all right. We need some more people to get on that. Just a heads up, those questions, they are a little tough, but that's because they're former AP Calc questions from the actual AP exam. So if you did okay on them, that's a good thing. If you didn't do okay on them, then that's still a good thing. At least you got to be exposed to them and see it. But anyways, all right. So we'll deal with that later. Let's go ahead and take a look at your derivatives and take a look at your problems here. So far, I'm a little concerned on your derivatives on some people. Oh, but a lot of you guys did pretty well. So check this out, right? You guys remember how to do the chain rule? if you have a function that has a function inside and the function outside, the derivative is just the derivative of the inside, right? Whatever that is. Derivative of x squared minus 4 is just 2x. Times it by the derivative of the outside, which is, that's a 2/3, not a 2. There it is. So derivative of the outside, which is going to be 2/3 times some stuff. But don't forget to subtract that from 1, right? 2/3 minus 1 is going to give you a negative 1/3. So that's what that function looks like. Okay, that's what that function looks like, right? And I'm sorry, that's what the breakdown is for the inside and the outside. Can I drop the pair deck? Or you guys? Oh, all right. I got you. Boom. There you go. As I was saying, right? This one right here. There we go. We just go ahead and stack them and multiply them all together here. So the multiply with the derivative of the inside, which is 2x, multiply that with the outside, which is going to be 2/3, right? I'm going to put that in some parentheses, times what goes inside there is x squared minus 4 to the negative 1/3. And that's my derivative. Now, this is the part where I got to kind of like get on your case about your algebra skills, because we're going to have to set this thing equal to 0. And if I leave it alone like this, it's not the easiest thing to solve. What you should do is, if you get something that's a little too complicated, like here, I'm talking too much here. Maybe if you just see it, I myself would not know how to solve this, setting it equal to 0, and then just going from there, right? That just is, I don't know what I need to plug in to make that equal to 0. And some of you guys are saying, not just 0. And you're right. That's one of them that is true. That is 0. But it makes it a little bit easier if you clean this up and rewrite this a little bit more, right? So for our critical points, we're supposed to set this thing equal to 0. And I'm going to do that by cleaning this up a little bit here. I'm going to multiply this out. So I have here 2x times 2/3 is the same thing as 4x/3. And then I'm going to rewrite this thing over here. This is a negative, so it's going to go in the bottom of my fraction. And it's a negative 1/3, which means it's a cube root of this stuff. And that's how I'm going to rewrite this. I'm going to rewrite this as 4x/3 times the cube root of x squared minus 4, and I'm setting this equal to 0. Okay? How you guys doing? Did I lose anyone here? Have I lost anyone on the first step where I took the derivative? Have I lost anyone on the second step when I rewrote it? I set it equal to 0. I need you guys to be honest with me, right? If you're lost at any point, you gotta let me know. Otherwise, I believe that you get it all, which is not a bad thing to do. Anyways, so let's go ahead and finish through here. When you're dealing with a rational expression, meaning a fraction, the only time a fraction can ever equal to 0, right? The only time a fraction, something over something, can ever equal to 0, the only time that can happen is if the top part is equal to 0. That's the only way. That's the only way. And the only way this top part over here is going to be equal to 0, right? The only way that this guy right here is ever going to equal to 0 is if, is if 4x is equal to 0. All right, so that's the first thing I'm going to try to solve here. That's going to happen when 4x is equal to 0, and that happens when x is equal to 0. That is one critical point that I've found, right? That's one critical point that I've found. There's a couple more. Anyone else know where else I can find critical points? It's not only when the derivative is equal to 0. It's not only when the derivative is equal to 0. Do you know where else critical points occur? You guys remember? Talked about this a couple times. Critical points don't only occur at where the derivative is equal to 0, but it's also where the derivative is not defined. That's right, Monica. It's where the derivative is not defined. So that's the next thing you need to be able to do here is look at this thing, and when will this function be undefined, right? And again, if you're dealing with a rational expression, right, this thing is undefined when the bottom is equal to 0. That's how you deal with rational expressions and seeing where the function is undefined, right? The function is undefined when the bottom is equal to 0. And if you look at this bottom part right here to see when does that equal to 0, Monica's already got the answer there for us. But yeah, that's right, Monica. It is going to be at 2 and at negative 2. Let's show the work for that, though, right? Let's show the work. You are right. You are right. But here, 3 times the cube root of, and again, whenever you're stuck on these types of problems, try factoring it out, right? In the bottom there, you're going to have here x plus 2, x minus 2, because you have a difference of squares there. And you're going to get here, when x is equal to negative 2 or positive 2, you're going to get something that's undefined, right? So it is undefined defined at x equals to -2 and x equals to 2. So those are actually your critical points as well. These are also critical points. So in this particular problem, you have 3 critical points that you're dealing with. All right, you're dealing with 3 critical points. And it's going to be a little bit ugly here, but let's go ahead. Let's write them out. The smallest critical point we have here is x equals to -2. The next critical point is going to be at x equals 0. And the last critical point is going to be at x equals to 2. So with that being drawn out, you have now 4 intervals to be dealing with, right? 4 intervals to be dealing with. You ready? The first interval I'm going to write down is just the ones that are between them, right? Or the first 2 intervals I have here. So -2 to 0 and then 0 to 2, right? And of course we have from 2 to infinity. And then we also have from -infinity to -2. Those are my 4 intervals that we got to deal with. And I don't know if those critical points are maximums or minimums or not, or if they're just, you know, points where they go flat, right? So I pick them out, I plug them in, and I calculate. And this is the part where it's like you plug it into this equation right here to see if it's positive or negative. And let's just see what happens here. So if I plugged in something like, for example, into the derivative here, what's the number that's between -infinity and -2? You guys have been trending with this one, so I'm going to go with -3 because that's what you guys seem to be doing, picking like 1 off from those intervals. So we'll go with that. So when I plug that in, I'll have here 4 times -3. And in the bottom, I have 3 times the cube root of -3 squared minus 4. Now, that looks like a monstrosity to simplify, but I don't care about the number, right? I'm hoping you guys are catching on that trend. When we're looking at the first derivative test, you're just looking at if it's positive or negative, right? So when I multiply the numerator here, you'll notice that I end up with a negative there. When I deal with the bottom over here, this right here is going to become +9 minus 4, which is still a positive number, which is multiplying with a positive number over here, right? I don't care what the square root of the cube root of 5 is. I just care that it's a positive value, right? And the positive value times this +3 is still positive. And when you have a negative divided by 2 positive signs, you're going to end up with a negative as your value. Are you guys okay with that? Do you guys see what I just did there? I multiply these 2 positives down here in the bottom. And then I'm going to end up with a negative divided by a positive, which gives me a negative result. And that's what I'm focusing on. The fact that I see that it's a negative value, right? That tells me that this function is decreasing on this interval. Okay? And we're going to do that for all of these. We're going to do that for all of these. And I'm going to, for the sake of time, I'm just going to give you these values. I really suggest you pick some numbers and you just practice doing this to see what those are, right? So from here, I would probably pick like -1 to test and see what I get. And you should be getting something that is going to be positive and increasing. I'm just giving you these values. You should test them out to see it. But yeah, it's going to be increasing on that interval. And then from 0 to 2, I believe the function will be decreasing. And last but not least, from 2 to infinity, this function is going to be increasing. You should really do this on your own time and test them out just to see if that is the case. But that is what's going to happen with them. And then knowing that it's decreasing, the increase, and that tells me that this right here should be a local minimum, right? And then increasing to decreasing, this tells me that this right here is a local maximum. And decreasing, increasing, this one tells me that this one right here is a local minimum. Okay? And those are your extremas for this problem. That's it. Those are the 3 extremas that you'll have on your problem there. And when you finish a problem like this, you could always, like for your homework's sake, you can always plug it into Desmos and see if that is correct. So I'm going to go do that real quick. Let's go plug it into Desmos real quick over here and just see what we get. I'm going to plug this function in like so. X squared minus 4. Of course, all this being raised to a power of 2 over 3. Let's take a look at this graph. My favorite thing, Desmos. I don't know if you guys are familiar with this. It's a free graphing calculator. Although you guys have the TI calculator as well. That's free on there. But here you go. Crazy looking thing, right? But it kind of makes sense, doesn't it? Look at the intervals that we have. We have from -infinity to -2, which is this guy right here. And then after -2, we go from -2 to 0. which is another critical point. So that's a second interval right there. The third interval we were dealing with was from 0 to 2. And then we dealt with from 2 to infinity. So you know what might actually help us to see this a little bit better is going to be these guys right here. All right, we got that interval right there. We have the other interval, which is x equals to 0. And then we have the third interval where x equals to 2. So there are the three intervals right there, if you guys can see them. Let's make them all green so we can see these intervals right there. There you go, right? And I'm hoping that this makes sense here. Let me cut this off and let's actually put this into the notes here. I just wanted to show this a little bit more, right? So let's put this over here into Desmos over here and put this off to the side right here. And no, let's put it underneath you. Yeah, let's put it underneath you. Let's put it underneath you. Let's go like so. And we can actually see those intervals, right? Actually, ooh. Let's line it up so that the green lines match up with the interval lines. That'll be neat to see. Come on. I got this. I'm wasting your time, guys, I know, but I just really want this to line up. Boom. There you go. Check it out. Check it out. You can kind of see it, right? Since the slopes are negative here, the function is decreasing there. And if you did the work here, this would be a positive slope, which shows you that the function is increasing. And then over here, after the critical point at 0, it's decreasing. And then after the critical point down here, it's increasing. So there you go. There you go. Isn't that neat? You can actually see it when you do the math here. So here's the thing, right? The function values are all positive here, but the derivative values are changing. It goes from increasing to decreasing and decreasing to increasing. And that's all you have to do to figure out if you have a local max or a local min. Okay? And some of you guys might say, "Nah, you could just graph it and you could find the local max and local min." And I agree. But knowing this, though, this is how we're going to be connecting, right, what we're doing with your derivatives and with functions. And when you have complex functions that are really hard to graph, if you could take the derivative of them or know what the value of the derivative is, if it's positive or negative, you can tell if something is trending up or trending down, which if you listened to any stuff about the coronaviruses that are going on right now, there's a lot of controversy going on right now about people saying, like, why are they reopening things when the number of cases is higher than it was when we went into shutdown in December? And when you're dealing with stuff like that, you don't actually focus on what the function value actually is, but instead you focus on whether the function is increasing or decreasing. Does that make sense? Right? If I was at this point right here, but I was trending downward, I'd be a lot happier because it's going towards a minimum. Whereas if I was over here, which is a lower value, but trending upward, I'm not happy with that because it's actually going in a direction that will be increasing as it keeps going per day. So just keep that in mind when, like, what exactly are we talking about here when we're dealing with this whole increasing and decreasing thing? It's just how the function is moving, right? And then when you find out that there's a critical point, you can now find out if those critical points are maxes or minimums. Okay? Are you guys feeling all right? Feeling okay? So, not okay? I'm going to put it on the pair deck right now. Can you guys tell me, how do you feel about this topic so far? Right? I just need to know. I just need to know. Is this like a thumbs up, thumbs down, or you're just like, I have no idea what's happening here? So just let me know here. I put it up on the pair deck. Just tell me, you guys feeling thumbs up on this so far? Or are you feeling thumbs down on this so far? Just move the dot. Be honest with me. I can't see your names on there. I just want to see if you're all right. But we are going to move on even if you aren't feeling all right. But if you don't feel okay about it, there's going to be practice problems on your homework. And then also, please, I can't stress this enough, that you guys really should stop by my office hours. And we could do some problems from your homework, right? Hopefully it'll make you feel a little bit better. Hopefully it'll make you feel a little bit better if we do some practice problems, okay? All right. Other than that, I'm also going to be assigning some more of those videos for you guys to watch. So hopefully that will help you guys out with this. Okay. All right, let's move on. And yeah, it looks like you guys are somewhere in the middle, but a little bit more trending towards the positive side. So that's a good thing. That's a good thing. There's a couple of you guys that are in the not okay part. And that's where you got to be honest with me. You got to come see me, guys. You got to come tell me, what is it that you're lost at? What is it that you don't understand? Or you can type it right now. We can talk about it right now. But stop by. Stop by. We should definitely talk about it and see how to do these problems. Okay. All right. All right. Let's move on. Let's go. Today, we're going to be talking about, first thing we talked about was the first derivative test. Next thing we're going to talk about is the, you ready for this? Wait, how big do I want this to be? Let me adjust my window real quick here. Yeah, that size. That's a good size. Let's talk about this guy. We're going to be talking about the second, my writing is not as good as it used to be, the second derivative test. Second derivative test. Okay. The second derivative test doesn't tell you if a function is increasing or decreasing. Instead, the second derivative test tells you about the concavity of it. Is it concave up or is it concave down? Are you guys familiar with that term, by the way? Concave up would be something like this, right? You see the concavity here? The concavity is facing upwards, right? Whereas if you have something that's concave down, it'll look something like that. That's terrible. Let's draw it like this. There you go. That's something that's concave down, okay? And when you're dealing with the second derivative test, it'll actually tell you if a function is concave up or concave down. And it's very simple. It's very simple. It's almost as simple as the first derivative test. In fact, I'd say it's pretty much the same. A function, right? A function is concave up, right? When the second derivative is positive. That's it. That's it. First derivative is positive. That tells you that the function is increasing. It's going upwards. If the second derivative is positive, it also tells you that it is concave up. It is concave up. And the second derivative also tells you when a function is concave down. And that happens when, you've probably guessed it by now, it happens, that's not how you spell function. A function is concave down, right? When the second derivative is negative. That's it. That's pretty much it. If the first derivative is positive, if the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. So you can actually have a combination of things that are where the first derivative is positive and the second derivative is negative. You get really interesting shapes, right? So if something is positive and I'm sorry, I'm saying too many words at once there. If a function is increasing and concave up, that means that that thing is accelerating very, very fast. See that? That's something this is something where it's increasing, right? And concave up. Now, you'll say, why is that any different from something that's increasing and concave down? If something is increasing and concave down, it looks like this, which is what I drew down there. This is something that's increasing and concave down. Now, why is that a big deal? You've heard this term. It's the idea of flattening the curve, right? Instead of having it go straight up like this, if you can get something that's still increasing but slow down its increasing, right? You create this shape that's concave down. So if something is still increasing but it's concave down instead, concave down, right? You'll be slowing down the rate at which it's increasing at, right? You're slowing down the rate of its derivative, which is the rate of its rate. Yo, dog, I heard you like rates. So you can actually see it affecting it. The second derivative, if it's positive or negative, will actually tell you how much the first derivative is increasing or decreasing by as well. And that's kind of, I think it's kind of neat. You can actually see it slowing down here. And we'll do more of these problems. But here, let me show you some more examples here. If you have something that is decreasing and concave down, why that thing is just going down very, very fast. Whereas if you have something decreasing and concave up, it's decreasing but slowing down to something like that, right, where it's flattening out at the bottom there. So this is something that's decreasing, right, and concave down. And this right here is something that's decreasing and concave up. right? So if they're pretty much, if the first derivative and the second derivative are opposite signs, right? It's still still following whatever the first derivative is doing. It's either increasing or decreasing. But if it has an opposite sign on the second derivative, it's slowing it down, I would say, right? Whereas if they were the same sign, they're shooting the speed is increasing in whatever direction it's going. Okay, that's the idea here when you're dealing with the second. That's why it's important to know about the second derivative, right? And its values there. Okay, so let's go ahead and let's do a problem to see where something has its what its concavity is. Okay, so let's go ahead and take a look at a problem here, and then we'll talk about the steps behind this. So let's take a look here at this example problem right here. Right, and let's say I was asked to find the concavities on, find the concavity of the following. Right, let's take a look at this concav. Let's take a look at this function here. Let's say the function I'm dealing with right now is going to be y is equal to 3 plus sine x on the interval 0 to 2 pi. I'm not looking at it for all real numbers. I'm just going to be looking at it from 0 to 2 pi. Okay? So from 0 to 2 pi, what is this? What does the concavity of this function look like? And we're going to be focusing on it, on its second derivative, right? So first derivative, right, is going to be equal to derivative of 3 is just 0. Derivative of sine x is going to be equal to cosine x, right? If I looked for critical points, I would set this guy equal to 0 and see where is this function increasing and where is this function decreasing. But I'm not asked that right now. I'm not asked about when is it increasing, when is it decreasing. I'm asked simply about its concavity. And when you ask about concavity, you're looking at the second derivative of this. So I need to take the derivative again. What's the derivative of cosine? That's going to be equal to negative sine x. Negative sine x. And the question for this is, when, right, does the second derivative change its sign? When does it go from positive to negative and negative to positive? Well, we need to see, when does this thing equal to 0, right? When does sine x equal to 0? It's like the same trick we did for the first derivative test. When we set it equal to 0, we found these things called critical points. And the critical points was perfect to see when a function changes from increasing to decreasing. When we do it for the second derivative test, though, it's not called a critical point, by the way. It actually has its own name, and we'll talk about the name in a second here. But we're looking to see when it's possible when the sign for the second derivative is going to change from negative to positive or positive to negative. And that's going to tell me when does it go from concave up to concave down or concave down to concave up. Now, when does sine equal to 0? Do you guys know how, do you guys remember your unit circle? Do you guys remember what values of sine between 0 to 2 pi is going to give you a output of 0? Do you guys know those? Not 1, never 1, never 1. How about this? What's sine of 0? Do you guys know what sine of 0 is equal to? What's sine of 0 equal to? What's sine of 0 equal to? 0, yeah. So 0 is one of my answers. What's another value? Sine of what else is going to be equal to 0? Anyone know? What's another value? That's in radians, by the way. Don't do degrees. All right, what else is equal to? What else will make sine equal to 0? Not negative 1. Not negative 1. You're thinking of the results, Monica. If you do sine of 3 pi over 2, that would be equal to negative 1, and sine of pi over 2 would be equal to 1, right? I'm asking, when is this thing going to be equal to? Oh my! Do we need to practice our unit circle, guys? Sine, cosine, and tangent, those trig values, you do need to know them. You need to know how to solve them as well, because there are multiple answers here. And your calculator is good enough to find you one of them, but not all of them. So let me just tell you right now. On the unit circle, right, sine is equal to 0 at 0. It's also equal to 0 at pi, right? Sine of pi. Yeah, Kaylee, that's right. It's at pi. You got it. And sine of 2 pi, right? It's equal to 0 at all those points. 0, pi, and 2 pi. And it just keeps repeating, by the way. It's also going to be like that at 3 pi, 4 pi, 5 pi, right? Because if you have a unit circle that looks something like this, sine is equal to 0 here and here, right? That's where sine is equal to 0. Cosine is equal to 0 here and here. Just in case you were looking for the critical points, when does the derivative equal to 0? It's going to happen at pi over 2 and 3 pi over 2, just to keep that in mind, right? Anyways, we're not focused on that. We're focused on the sine value here. And I'm looking at this on the interval from open interval from 0 to 2 pi. So that means I'm not caring about x equals to 0 or x equals to 2 pi. The only point that I really care about is that x equals to pi. That's the only place that I really want to focus on, right? So that actually gives me an interval that I'm focusing on here. I'm focusing on the interval from 0 up to pi, and then from pi up to 2 pi. I'm going to be testing this out to see if it's positive or negative in the second derivative. Okay? So what's the number that's between 0 and pi? That's easy to calculate with trig functions, right? Which trig functions? This is where you got to, make sure you guys are up to your game on your trig functions and your values here. And an easy number that's going to be easy to plug in between 0 and pi, right, is going to be pi over 2. How do I know that? Again, it's just your skills with your unit circle will help you out on this problem. Okay, so pi over 2 is a number I'm going to test into my second derivative right here to see if it's positive or negative, to tell me if the function is concave up or concave down. Okay, so let's take a look here. I'm going to be looking at negative sine of pi over 2. Well, sine of pi over 2 is, well, if you looked at the unit circle I drew earlier, is going to be positive 1. So it's going to be negative, and sine of pi over 2 is a positive 1. So negative positive 1 is going to tell me that the sign I'm going to end up with a negative sign right here. And that tells me that the function is concave down. The function is concave down. Okay? Do the same thing over here. Pick a number that's between pi and 2 pi. What's the number that's between pi and 2 pi? Did anyone catch what I said earlier? 3 pi over 2. That's right, Shirley. That's right. That's good. 3 pi over 2. Test that number to see what you end up with. So I'm going to be plugging in to negative sine of 3 pi over 2. Negative sine of 3 pi over 2. Well, sine of 3 pi over 2 is not positive 1. It's actually negative 1 because it's at the bottom axis of your unit circle, right? So negative times negative right there is going to give me a positive sign, which tells me then that this over here, the function, is going to be concave up from pi to 2 pi. Right? So now if I were to do this and combine this and find out what my critical points are to figure out where my max and my min occur, I can also find out what my concavity looks like. And you can kind of picture this shape of this graph without actually graphing it. But let's actually just go ahead and graph it and just take a look at this part where it's concave up and where it's concave down around this part where x is equal to pi. Okay, so I'm going to go back here to my graphing app over here. Let's go ahead and graph this guy here. Let's take you out, take you out, take you out. New function we're going to be focused on right now is 3 plus sine x. 3 plus sine x. So 3 plus sine x. There's my graph, right? And I'm going to be focusing on this around the labels of, let's say, let's go with pi, right? There we go. All right, so I'm going to go from 0 to 2 pi, right? 0 to 2 pi, that's about there, yeah? But I'm going to put into place here x equals to pi, which was my new point that sees where it goes from concave up to concave down. I'm going to go ahead and screenshot this real quick here. Give me 1 second. So I'm only going from 0 to 2 pi, which is from there to there. Let's go ahead and put this into here. Check this out. Check this out. So can you guys see it? See the word concave up right there? Do you see how right here you can clearly see the bowl is concave up? See it? And then you can see over here where it's concave down between 0 and pi. It's like so. Weird, right? Well, not weird, but I mean, makes sense, right? Hopefully it does. And you can kind of see, right, what the function is doing with this concavity. This point right here, this x equaling to pi, has a special name. When concavity changes from concave up to concave down, we call that right there a point of inflection. Point of inflection. That's what we call that. A point of inflection. It's where it changes from concave up to concave down. And that only occurs when the second derivative is changing from positive to negative or negative to positive. All right, let me give you the steps for what we just did today, or for this part right here, okay? So I'll leave this up right here for you guys, but here we go. Let's say I'm gonna zoom in a little bit here, I'll put that back up in a second here, but let's say I was asked to find, right, points of inflection. To find points of inflection. Not that crazy to do. Step 1, find the second derivative. Find the second derivative. Step 2, set the second derivative to 0 and solve. This will help you find possible points of inflection. They're not guaranteed, right? Whereas the other one for the first derivative test, when you set it equal to 0 and you solve it, those are called critical points. They are a critical point in the problem. For the second derivative test, when you set it equal to 0 and you solve, just because you find the answer, it's not a guaranteed point of inflection. It's only a guaranteed point. It's only a point of inflection if the sign changes around them. If it goes from positive to negative or negative to positive, we call that a point of inflection, right? What we're finding right now when we solve it is seeing that it is a possible point of inflection. Step 3 is the last step, which is basically what you saw me do, which is test values around possible points of inflection. And that's it. That's all you got to do these concavity tests, right? You just have to take the second derivative, set it equal to 0, and then test points around it. And once you test those points around it, you can see if it's increasing or decreasing. I'm sorry, if it's concave up or concave down. And if you combine that with your first derivative test, you can see if it's increasing or if it's decreasing, and so on and so forth. Okay? How you guys feeling? Don't worry if you don't know how to do it yet, because I just showed you one example. But does it kind of make sense, right? If not, can you just stick this in your mind and just remember concave up, concave down, right? If the second derivative is positive, concave up. If the second derivative is negative, concave down. If the first derivative is positive, that doesn't tell you if it's concave up or concave down. That just tells you if it's increasing. Or if the first derivative is negative, it tells you that it's decreasing. So I'm going to start off on this problem right here. I don't think I'm going to be able to finish it, but we should get started on it. So I'm going to go ahead and do another example. And we're going to combine both those concepts into one problem. You guys ready? Probably not, but we're going to go into it anyways. Okay? We're going to get into it anyways. So let's go ahead and try this problem here. Let's say I was given a function. F of x is equal to 2 times x to the 4th minus 16 times x to the 3rd. All right, here are the directions for this one. We're going to be asked to find the intervals where the function is increasing, decreasing, concave up, and concave down. Right? Concave up and concave down. So we're finding 4 things here. We're finding when it's increasing, when it's decreasing, when it's concave up, when it's concave down. All right. So to find out when the function is increasing or decreasing, right, these guys right here, that's going to be using the first derivative, right? That's going to be the first derivative test. That's this guy right here. So basically take your function, take the first derivative of it, and that'll help you out right here. So f prime of x, go ahead and take the derivative of that guy right there. 2x to the fourth minus 16x to the third. I'm going to end up with this right here. This is going to be equal to 8x cubed, right, minus 48x squared. Whew. All right. Help me find the critical points. Remember, critical points is going to happen when the first derivative is equal to 0. So I just take this first derivative right here, this 8x cubed minus 48x squared. I just set it equal to 0. That's it. That will help me to find my critical points. Have you guys know what the step is to solve this guy? This is not a quadratic. It is a cubic now, right? What's the step? What's the thing that we need to do to solve this? What would you guys do? Help me solve this. I want to test your algebra skills here. Factor out an 8x squared. That's beautiful, Monica. That's called factoring out a common factor. That's a standard technique. You try to make it into a lower power so it's easier to solve. 8x squared is something that is in common with both of them, so I'm going to be left behind with just an 8 right here minus a 6 right there. And if you're struggling to see how I got that, please let me know. Right, that is an important skill. You do need to know how to solve these higher degree polynomials. Okay. Doing so will give me that 8x squared is going to be equal to 0, or x minus 6 is equal to 0. So I have two possibilities here for my critical values. X is equal to 0, or x is equal to 6. Okay? With that, we need to figure out when is it increasing and when is it decreasing. We just use our signs, right? You got two intervals here, right? Or actually, I should say we have three intervals here. Is it two intervals? Wait, is it just two intervals or is it three intervals? Knock me, what's going on here? It's hard for me to see this if I don't actually draw it out. So let me, you know what? Why am I trying to shortcut this? Well, I'm going to just draw this out. I have here x equals to 0 is 1, and then x equals to 6 is another, which gives me then, yeah, three intervals, right? From 0 to 6 is one interval, from 6 to infinity is another interval, and from negative infinity to 0 is a third interval. So let's go ahead and test those out. Yeah, thank you, Monica. I don't know, I was trying to blank in my mind so hard right there, but that was hurting my brain just a little bit, right? Just a little bit. Okay, what are you doing? All right. So I got to test these points out to see if they're increasing or if they're decreasing. I just pick numbers and I plug them in, right? So I'm going to be plugging it into, again, if you plug into the derivative, you're going to be dealing with very large numbers, right? Which, you know, is fine if you want to do it that way. I'm going to try plugging it into the factored form. I think it's a little bit easier. And let me show you why I think it's a little bit easier. Let me pick a number that's between 0 and negative infinity. I'm going to go with like -1, right? So I'm going to plug that into here. I'll end up with 8 times -1 squared times -1 minus 6. 8 times -1 squared. This right here is going to come out as a positive number. This right here is going to come out as negative, which tells me that this guy is decreasing because I'm going to end up with a negative number there. Decreasing, right? Do the same thing for this one here from 0 to 6. I'm going to pick 1 and plug that in. So I'm going to have here 8 times 1 squared times 1 minus 6. Again, this is going to be a positive sign. This is going to be a negative sign. This is also decreasing. This is also decreasing. So now I have my intervals, by the way, right? It's decreasing not from negative infinity to 0 and then from 0 to 6. I mean, actually, that's exactly where it's decreasing. But at x equals 0, I don't have a local minimum. I don't have a local minimum. Do you see that? It's decreasing, and then it flattens out here, and then it keeps decreasing. And that's okay. That happens. That happens. All right, let's pick a number from 6 to infinity, and let's go ahead and almost wrap this up here. This is going to be, what's the number from 6 to infinity? Let's go with 7, right? And I'm, again, plugging it into here. 8 times 7 squared times 7 minus 6, which tells me that these numbers right here is positive. This right here is also positive. So this is going to be increasing on this interval. And it's increasing, which means that this right here is actually a local, since it's decreasing and increasing, I have a local minimum here. I have a local minimum there. Okay? At x equals to 6. And nothing else is happening. Everything else is fine, right? So it's decreasing, decreasing, and increasing. So I found out the intervals where the functions are increasing and decreasing. Next thing you need to do is find out where the function is concave up or concave down. Okay, which means then I need to take a second derivative test. Second derivative test. And that just means I need to take the second derivative, right? That's where this comes into play, by the way. If you're talking about concave up and concave down, that just means you take a look at the second derivative. And that's easy to do because I already have the first derivative right here. All right, so take the second derivative, just go on to the next one, f double prime. That's going to give me 8x cubed. Right, so that's going to come out as 24x squared minus 48 times 2 is going to give me 96x as my second derivative. I'm looking at the time right now. I'm going to run out of time right here. So I'm going to just finish this up right here and ask you guys to do this part on your own. Can you go ahead and figure out what are your possible points of inflection for this guy right here? 24x squared minus 96x. I'm going to go ahead and set that equal to 0. I'm going to ask you guys to solve that nice quadratic there and see what your possible points of inflections are, and tell me where's it concave up and where's it concave down. All right, guys, I'm gonna start posting up. Actually, now I posted up homework earlier, but the part that asks about the concave up or concave down, you were not able to do yet. But now that you see what you need to do, you can go ahead and start doing the second part of that homework. Not the second part, just the remaining problems that are on there. Okay, guys. And that's going to be it for today. We'll cover more when we come back on Thursday. I know this is a lot, so don't think that we're done with this, okay? So we're going to keep practicing this until you get more comfortable with this. Anyways, guys, that's it. I'll see you guys on Thursday. Have a good rest of your day. Yeah, I'll see you guys later, guys. Have a good one. See you guys.